everybody, welcome back to my R companion series for my Monte Carlo simulation video series. In this video, we are going to implement some of the things we just learned about simulating values from univariate discrete distributions. The example I'm going to use throughout today is going to be the geometric distribution with parameter p. There are two geometric distributions, one that starts from 0 and one that starts from 1. And we're going to look at the one that starts from 1 here, and its very minor adjustments to simulate from the other distribution. Now you might be asking at this point, isn't there a built-in function in R to sample values from the geometric distribution? The answer is absolutely yes, there is. There is a built-in function to simulate from all of the nice known named distributions that you learn about in a first semester in probability and statistics, like the geometric distribution, the binomial distribution, the Poisson distribution. On the continuous side, the normal distribution, the exponential distribution, the gamma distribution, and many more. But the point of this course is to know how to construct these algorithms. And outside of using the built-in random number generator, I don't want to use any more black box algorithms, if you will. Because what is going to happen to you if in your work, your research, your classroom environment, you are suddenly asked to simulate from a distribution with a given probability mass function or probability density function, and it's not one of the nice known named distributions, because it's easy to come up with a valid probability mass function that doesn't look like one you've ever seen before. So we want to know how to do this from scratch. For the geometric distribution, we had a really slick way to simulate values involving a ceiling function and the natural log. I am not going to focus on that here today. If the video is not too long, I might slip it in at the end. Instead, I'm going to focus on the more useful algorithm of interval chopping, because that natural log and ceiling function thing will only work for the geometric distribution and not for other distributions. So recall the interval chopping technique. Suppose that x has a geometric distribution with parameter p, and this indicates the geometric distribution starting at 1. This is my notation only. I don't see anyone else ever using a subscript like this. The probability mass function looks like this, and so we have that the probability that x equals 1 is p, the probability that x equals 2 is p times 1 minus p, etc. The interval chopping technique says grab one value drawn from your random number generator, a realization of the uniform 0-1 distribution, and start looking at the various probabilities on this interval from 0 to 1. If the uniform is between 0 and p, that happens with probability p, and so we will output the number 1 because we want the number 1 to occur with probability p. If not, we then should check whether the uniform being greater than p is within the next interval of length p times 1 minus p. So we're going to go from p up to p plus p times 1 minus p and check whether or not the uniform is in this interval. If it is, we'll output a 2. If not, we will proceed and add to this endpoint a p times 1 minus p squared and potentially output a 3, and so on. Note that as we write down code for doing this, if we have not found that our uniform falls in this interval here, then when we go to check this interval, we really don't have to check whether it's between these two numbers. We already know it's greater than this number. So at all steps, I will be checking whether the uniform is less than something. Whereas in theory, we should be checking that it's between two numbers. But again, the fact that you have moved up to the second right endpoint already implies it was greater than the first right endpoint. Let's get to coding. I've got R open here. I happen to be working in Windows today. This is the R console with a ridiculously large font. And this is a blank script that I have already called geometric.r and saved in the working directory. If you don't know how to form a script or know anything about working directories, you might want to check out my last R tutorial that I will link right here. But if you're ready to go, let's do this. The first thing I'm going to do in my script is set a value for p. I am going to use this assignment operator where I create an arrow. You can use an equal sign, and I'm just going to choose, for this example, p equals 0.3. Also remember that spaces are not important in R. I just left space between various things I typed here to make it a little easier to read. I'm going to hit enter and nothing's going to happen because I'm not in R right now. I'm just in a text editor. Once we get all of the code that we want to run over here, we'll call the script over here in the console window. Now, the next thing I would usually type is something to define the number of reps, or maybe we'll call it n. And, as I always choose n to be 100,000. I am not going to do that yet. I'm just going to focus on simulating one value from the geometric distribution, and then we'll go ahead and put some kind of loop around that and try to get 100,000 values. So to do this, I need a value drawn from the random number generator, a realization of the uniform 0-1 distribution. I'm going to call this U, and then my assignment arrow. To call the random number generator, you type runif for random uniform, open parentheses, in this case 1 and close parentheses. The number 1 means this is the number of uniforms I want. Now the first thing I want to check is whether this uniform is between 0, it's definitely greater than 0, but between 0 and p. And then if it's not, I'm going to add more to that and add more to that. And I'm essentially building up a CDF, or cumulative distribution function. So I think I'm going to call that right endpoint of the intervals in interval chopping, I'm going to call it CDF. And I could start this with 0, but the first value, might as well get started. The first value is p. And if the uniform is less than or equal to p, which is now the value of the CDF, then we're done and we'll have to output the number 1. So let's go ahead and type output. This is just the name of, my variable. You can call it whatever you want. I'm going to assign that to be 1. Again, if the uniform is less than or equal to p, in other words, if u is less than or equal to the CDF, output should be 1 and we'd be done. But the uniform is not always going to be less than or equal to the CDF. So let's continue, assuming it's not. If it's not, I want to add more to the CDF to move from p to basically p plus p times 1 minus p. And then after that, p plus p times 1 minus p plus p times 1 minus p squared. So I want to do this not for a fixed number of times, but I want to do this until I get what I want, which is the uniform less than or equal to the CDF. For this reason, I'm going to use a while loop. This is something that will continue for as long as an event that I'm looking for has not happened. So as long as my uniform U is greater than the CDF, because if it was less than or equal to the CDF, I want to stop. But as long as the uniform is greater than the CDF, I want a series of commands. And I'm going to enclose these commands in an open and close curly bracket. And I'm purposely not putting this open bracket down here. If you do it, you'll be fine. But you can run into some issues using brackets in conjunction with other commands, because R is going to read and execute your code line by line. And if this line of code here was executable, if it was a complete command on its own, let's copy and paste it and see what happens. I'm going to copy and paste it into my console window. I'm going to hit enter. So my normal prompt, I don't know if yours is going to be exactly the same, but my normal prompt is this right arrow caret thing. And if my line of code had executed, I should have another right arrow caret thing. But what I have is a plus sign, and that's saying, please finish your line. Tell me what else to do. And so at this point, R would continue reading the code that starts from this bracket and finishes at this bracket, and everything is going to be fine. But if this line of code was somehow something that was a complete line of code on its own, then R is going to execute this command and then have all of your other stuff just like tacked on afterwards. In other words, it's not going to know what to do while U is greater than the CDF. In this case, you are fine, because when you type while U is greater than the CDF, it's not enough. It's already waiting for you to type more. So I don't know if that made sense, but I like to put my opening bracket at the right side of lines like this in order to say, you know what, I've got more coming. I've got more coming. Please do not try to execute this line without waiting. Okay, so what should we do in here? I want to output, I don't want to output anything. I want to increment the variable that I've named output by 1. So I could type something like output is output plus 1. But I think that it's going to be a little nicer if I define a new variable. It's just going to be an integer value like I or j would be something nice to use. I'm going to use I for something else later. I'm going to define it to be 1. It's exactly the same thing as output. And maybe it's not it doesn't make a lot of sense to you why should you have extra variables? I do think something is going to be cleaner in the end when I try to put a big loop around this. So what I'm doing right now is totally up to you. But in the while loop, I'm going to say, update j to j plus 1. And you could say update output to output plus 1, but I just didn't want to overwrite that yet. And then I need to increment the CDF as well. So my CDF is going to be my old CDF plus p times 1 minus p raised to the j minus 1. So remember, our CDF started with p. This is like on our interval, checking whether the uniform is between 0 and p. If not, you want to look between p and p plus. So here it is, p plus. And then j is currently 2. So we would be adding on p times 1 minus p to the first power. That's that probability that x equals 2. So we're incrementing our CDF by the next probability. And we are good here. I think I'll take out some of this extra space. So in the end, you're eventually going to get kicked out of this loop, and you're going to define output to take the value j. So this looks good. I think we have done it. I'm going to save this. For me right now in Windows, this is Control S. It may be Command S for you or something else. I'm going to go to the console window. And note that I'm in the middle of a command, so we need to stop that with something like Control C, Command C. In this particular graphical user interface, I do have a stop button up here. Anything it takes to get back to just a beginning prompt. And I'm going to type source, open parentheses, open quotes. My script is in a file called geometric.r. Close those quotes and close those parentheses and hit enter. So nothing has come up on the screen, and that's because I didn't tell in the script, I didn't say to print anything out. But over here, if I type output, it should have a value, and the value is 2. Let's use the up arrow to run the source command again, and the up arrow to get the output again. So it happens to be 2 again. Let's try this one more time to see if we get something different. Okay, now we have 8. So you expect to see any positive integers coming out here. And let's now produce a whole bunch of them so that we can look and see if the proportion of 1s is really 0.3, if the proportion of 2s is really 0.3 times 0.7 or 0.21, and so on. So going back to my script, at the top, after I defined P, I'm going to define my number of reps. So I'm going to call it N, and I'm going to choose 100,000. I am then going to put a for loop around the rest of the code. I'm going to say for, open parentheses, and I need an index variable. This is where this is what I saved my I for, I in. So I want I to go from 1 to 100,000, and the way to say that is 1:100,000. Close those parentheses and open curly bracket, which I'm going to keep on the same line for reasons I've discussed, and go all the way to the bottom and close that curly bracket. Now, currently, I am just overriding the variable output at every stage. And so if the first value produced by this is, say, 2, I'm going to have 2 100,000 times. Let's go back up here and define output as a vector so we can store each value that we get as we run through our for loop. I'm going to say output, and I'm going to assign to it, I'm going to rep a bunch of zeros. Repeat 0 100,000 times or n times. And then within the for loop, I do want to make sure to change each instance of output here and here to be output at repetition I. And the code is complete. Just to make this a little cleaner, I think I will go in here and indent a little bit. I don't have to do this. But we are finished. So save your source code. I'm hitting Control S. I'm going to go over here. I'm going to up arrow twice to get that source command again and hit enter. So now if I type output, I have a list of 100,000 values. I can't really tell anything. So let's see if the estimated probability of getting a 1 is really 0.3. I want to find the proportion of 1s in this list, so I'm going to type length of output. Now, if I just close the parentheses and hit enter, I will get 100,000. But I want to just look at where output is 1. So I'm going to put the square bracket, which you can kind of read as such that. Give me the length of the output such that the output is double equal sign is equal to 1. Close the bracket, close the parentheses, and we get 30,000, in this case 30,062, which is going to be a proportion of 0.30062. Let's get that proportion by hitting the up arrow and then continuing this command by dividing by 100,000, or just to keep this a little more, not dependent on magic numbers, the length of the output. So that looks good. We discussed in the last video from the main Monte Carlo series a way to look at a sort of confidence interval here. The P in this particular case right here is the probability of getting a 1. And that's already defined as 0.3. And we could look at P minus 1.96 times the square root of P times 1 minus P divided by N, which is 100,000. And that is the low value that we could potentially see and still think that everything is working well for our estimate for 0.3. And then if I hit the up arrow and change this to addition, that is the high end. So our simulation should be producing an estimate that is between 0.2971597 and 0.3028403. And it worked. It passed. Just to look at one more, the probability that x equals 2, our estimator for that, I'm going to hit the up arrow until I get that length command back and change this to a 2. So the proportion in our sample of size 100,000, where we saw 2s, was 0.21183. That value should actually be 0.3 times 0.7, which is 0.21. So this one looks pretty good as well. If I wanted to redo this confidence interval thing, the current value of P is 0.21. That's not to be confused with the P here for the geometric distribution, but if you followed the discussion at the end of the last Monte Carlo methods video, you'll remember I did some quick and dirty confidence intervals. And so I need to, if I want to redo this, then I need to redefine P, which I think I'm actually okay with right here because I don't think I'm going to need it again in the rest of this video. So I am just going to redefine P to be the probability of getting a 2. And now I can simply use the up arrow to get those confidence intervals back. And what we're expecting is 0.21, but anything between 0.2074755 and 0.2125245 for a sample of 100,000, of course, is acceptable. Our probability that we saw, our proportion, was 0.21183, and it is in fact between these two numbers, so we did good. Remember, sometimes it won't be in the interval. This is a rough 95% confidence interval based on the central limit theorem. If you got a value that was not in this little sort of confidence interval, you might try your simulation again and make sure it's not like systematically always above or below. And then it starts to fall in there and you're not seeing anything systematically weird. Okay, so to finish off this video, I am going to make a histogram of our results. We could start by writing hist output and then comma prob equals t for true. That's how we get the density on the y-axis instead of the counts. And we will see something like this. For this example, I really want to see each and every value on the x-axis because it appears that the width of these bins are 2, and I want to see a rectangle for each number over each number. So I want to see a rectangle centered at 1, which means I'm going to start it from 0.5 and go up to 1.5, and then one that goes from 1.5 to 2.5 centered at 2, and so on. So I am going to define breaks. First, let me type max for my output to see how high I need to go. 36. That's really high for this geometric, but this is fine. I'm going to define a breaks vector to be the sequence from 0.5 up to 36.5 in increments of 1. Now I'm going to hit the up arrow twice to get back, or 3 times to get back to my hist command. And I'm going to add comma breaks equals BR. So now I have a rectangle for x equals 1, for x equals 2, and so on. And we could do our little confidence bands on each rectangle. The video is getting a little long, and I think I'll just do a quick check by putting a dot on the top of each rectangle. So let's compute the coordinates of such dots. The x coordinates are going to be the center of each rectangle, which is going to be 1, 2, 3, up through 36. And the y coordinates are going to be p, which is 0.3, and then p times 1 minus p, and then p times 1 minus p squared, and so on. There's probably a more clever way to do this, but I am just going to put this in a loop. So I'm going to define p to be 0.3, and then let's say the y coordinates for these points. I'm just going to make a vector of length 36, and then I'll say for I in 1 to 36, assign the ith value of the y vector to be p times 1 minus p raised to the I minus 1. Close those brackets, hit enter. My x coordinates here are going to be, is going to be the sequence of numbers from 1 to 36. Oops. And now if I plot each x and y pair, I'm going to do that with the points command. When you type points, open parentheses, give some x coordinates and y coordinates, those will plot points on your current open graph. So I'm going to say x comma y. And yeah, let's hit enter. Okay, so I have some points. Those are a little hard to see. I am going to redo the points command, and I'm going to hit comma PCH. And so this has to do with the kind of character that you are using for your points. I want a solid dark circle, which happens to be character number 19. You could easily Google this and look for point plotting symbols in R. And so now I have solid points, as you can see. And, it looks okay. I'd rather see like this one be a little higher and this one be a little lower, but it's not bad. In fact, I've got a moment. Let's run the whole source code again and see if we can get something better. Here's a new plot, and I'm going to just type the same points command. Okay. Well, this one looks better. So I think we have simulated pretty well from the geometric distribution with p equals 1. In the next video, if you are watching these R videos in the right order with the main series, we will be talking about algorithms for simulating from univariate continuous distributions, and I hope to see you there.